Welcome students. Now in this video we are going to see the next metal forming process, that is the forging operation. So what is forging operation? So it is a process in which the material or metal is heated and then the force is applied to manipulate the size and shape of the component or that metal. This is the forging operation. So here first we heat the metal. First metal is heated and then force is applied to manipulate the metal to get required size and shape or shape and size of the component. This is the forging operation. So and the stresses induced here are of course the pure compressive stresses are going to induce into the material. See, the forging operation is one of the oldest metal forming process which is known to the mankind since the Copper Age. And this forging operation can be have the hot forging operation, or sometimes we can use the cold forging operation also. Now very important characteristic or property of the forging operation, that the manipulative ability, isn't it? The manipulative ability to control the grain flow. So that is very important thing for the forging operation. Please remember, because of this manipulative ability to control the grain flow, we can get the best mechanical property in the specified direction. That is very important characteristics of the forging operation. So required orientation of the grains can be possible. Because of that, wherever and whatever good mechanical properties we want to impart in the product, we can easily get. Now, as already we discussed in the beginning of this topic, that in all the metal forming processes, the limitation of the all metal forming processes, that we can go for the uniform kind of shapes in all these processes. But see, forging is only the metal forming process where up to certain extent we can able to produce some non-uniform shapes of the component. Please remember, by using forging operation only we can able to have some extent of non-uniformity in the shapes of the product. Okay, but the limitation of the forging itself is that we require the huge amount of forces and the power consumption. Please remember, if you require the higher amount of forces, to produce that higher amount of forces or load, we need to have that much amount of power consumption. So the force and power consumption is quite high in the forging operation. Okay, so let us see what are the classification of forging. So forging is basically classified into, say, the hand forging. There are two types we can have, and the another is machine forging. Okay, so hand forging, whatever the force for the deformation of the part is given with the human hands. Okay, so generally the drop hammers we can use here for the force. So that's why these are the hand forging operations. But when we look at the example of this hand forging, that is the blacksmith operation we have seen. Okay, now if you look at the machine forging, so in machine forging we are having the press forging, isn't it? The press forging. So see, in press forging, here the forces are applied by the drop hammers. Okay, so the impact forces are going to form. So but these forces are sudden, and the kind of forces impact force is going to apply on the product. But in press forging, whatever the force is applied on the component is not the impact force, it is not a sudden force, but it is the simultaneous force. It is simultaneous force. Please remember. Okay, so this is actually the press forging, and we can directly have the drop forging. Please remember, drop forging and press forging, these are the main classification that we have, and these are actually the closed die forging operation. In both the operations, the closed die is going to use. When in case of die forging, the material is kept on the, or the billet material, that is raw material, is kept on the lower die, whereas the press forging, we are keeping the material into the die. Okay, so that is the basic difference. And the force applied in the drop forging is sudden force, the impact force, whereas the press forging, we are having the simultaneous force. So simultaneously we are applying the force for the deformation of the material, not instantaneous or impact loads. Please remember this. Now, based upon the shape of the product obtained into the die, we are having the classification for forging operation is that for the press forging I am saying. So in that we are having, based upon the method of shape obtained, we are having number 1, open die forging. Second, we are having closed die forging. Third, we are having semi-closed. And fourth, the bar forging. Let us see it one by one. So open die forging, that is very simple. If the metal is kept between the two closed dies, and if we apply the force to get the deformation, so in open condition we are applying the force, isn't it? So this is the open die forging, that is between these two dies we are simply applying the force. Out of this, say this is lower die is stationary and this is a moving die or moving platen. Die is also known as the platen, and here is the material. Okay, we are applying the force. So this is open die forging operation. Then the next is what? We are having closed die forging operation, that is, say this is the die, upper die, and this is the lower die. So here the material is kept in the lower die, isn't it? And now you are applying the force. So this billet material is going to flow at each and every corner in the die when the die are meeting together and the entire surface here is closed like this. After some time the die will be like this. Okay, so that this billet material will flow to the each and every corner in the die. So this is the part will be get like this. So this is what? In closed condition, isn't it? When the two dies are closed. So this is a closed die forging operation. Okay, this is the second. This is first open die forging. This is second closed die forging. Now the third is what? We are having, that is semi-closed. No doubt we are having the die for doing the work, okay, but here the forces are applied in the open condition just by changing the position of this billet material in between the strokes that are given by this say hammer or that die, okay. So whatever the shape on the product is obtained by the die, which is having the shape on the die, the same shape we are going to obtain on the material. The thing is that here, by using this closed die only, the forces are applied in open condition by changing the position of the billet in between the strokes. So that is why the name is the semi-closed die forging operation. Semi-closed die forging operation. This is the semi-closed die forging operation. And the last one that is we are having, this is third one, and last one is bar forging. So whenever we are going to have the very large components, so definitely if your component is very large, to deform this component in the forging, you need the large amount of forces and power consumption, isn't it? Large amount of force and power to get this force, isn't it? So in that case, what we are doing, instead of forging the product or component at a single stroke, we are going to have a little forging of that part separately, okay. So instead of having the entire component forging at a single stage, at a single blow, we are trying to have the number of steps, number of passes, number of blows are required. हम ऐसा करते हैं कि भाई छोटे छोटे पोर्शंस को फोर्ज करते करते ये बड़ा जो लार्ज कंपोनेंट है उसको फोर्ज किया जाए. So that technique, instead of forging the entire part at a single stage, now we are going to forge little quantity of that part, and using this little amount of forging we get this entire component. This is known as the bar forging, okay. So these are the techniques based upon the method of shape obtained by the positioning of the component. So this is open die forging, closed die forging, it is semi-closed die forging and bar forging. So this is the basic classification of forging process. Now we are going to see the analysis of forging operation. The analysis of forging. So for that, say I am taking here this top die which is moving. We are having the cylindrical billet here, and it is the bottom die or stationary die, okay. So this is top die, this is bottom die, and this is our cylindrical billet material or raw material is there. So see here, in the initial condition of the forging, when the force is applied by this top die onto the workpiece, so there are the outward expansion forces and the inward frictional forces onto the interface between the die and raw material. So initially क्या होता है वहाँ पे, when the force applied by this top die onto this raw material or billet material, so at the interface of this raw material and this billet, there will be the outward expansion forces and inward frictional forces are going to exist. So here these inward frictional forces actually are greater than the inward frictional force is greater than outward expansion force. So because of that, what is going to happen? The raw material or this billet material is going to stick on the die surface. Okay, and when say the die is moving towards the center of this height of the component, so what is going to happen? See, now the outward expansion forces goes on increasing, whereas the inward frictional forces are the same. So here what happened, as these outward expansion forces goes on increasing, when the die is coming down, so there will be the bulging of this cylindrical raw material. Okay, bulging means what? The diameter is going to increase at the middle. That is the barreling also. क्या बोलते हैं इसको? Bulging or barreling will be there. Barreling. Because of the outward expansion forces goes on increasing. Now see, this first part or first initial condition of this forging operation, we can call it as the sticking condition, where the material is stick on the die surface and bulging occur. Okay, so the first part of the forging operation can be analyzed by the sticking friction model. कौन सा? Sticking friction model. Sticking friction model. Okay, now see the the die now moving ahead to get this billet material forged. So what is happening at some moment or at certain time, what happened? The outward expansion forces are become more than these inward frictional forces. Okay, पहले क्या था? इनवर्ड फ्रिक्शनल फोर्सेस जो थे वो एक्सपांशन फोर्स से ज्यादा थे. इसकी वजह से क्या हो गया था? दिस मटेरियल क्या हो गया था? ये डाई सरफेस के ऊपर स्टिक हो गया था. ओके, और इसकी वजह से एट द एंड्स इट वाज गेट स्टिक टू द plate or the die, and there is a occurrence of barreling or bulging. But now what happened? After a certain time, the inward frictional forces are stationary, they are constant, but the outward expansion forces goes on increasing. That's why what is going to happen now? The material is now going to slide. Material is now going to slide over the die surfaces. Okay, and because of that, now we are going to get the straight cylinder. See, pehle there was a barreling. At ends, the material was sticking to the die surface. Now what is going to happen? Now because of this outward expansion forces are more now the material is now going to slide over this surface of this die, and we are now getting the straight cylinder, isn't it? Okay, so now bulging is disappear and you are getting the straight cylindrical surface, cylindrical this workpiece having the changed dimensions. That is, now this, suppose original diameter DO was there initially, original height was there initially HO. Now the diameter becomes D final and height becomes H final. So you can see, because of this upsetting, this is nothing but the open die forging. Between the two dies we are compressing or deforming the material. This is the upsetting process. So definitely there will be the decrease in the height and increase in the diameter. Okay, so this second part of this forging operation is known as the sliding. Okay, and this second model, the sliding model, can be analyzed by the sliding friction, model. Okay, So always the forging operation can be analyzed by the sticking friction model first and then sliding friction model. See, because of this, that is the initially inward expansion forces are more than outward expansion forces, we are getting the very accurate dimensions in case of the forging operation. So this is about the basic thing about the analysis of the forging, on which base we are doing the analysis, that is, these are the two conditions. Okay, now see, one more thing I want to discuss here, that is about the open die forging and closed die forging operation. See, as this operation, as just now we discussed, is was a open die forging operation, but when we talk about the closed die forging operations, okay, so I want to talk about the volume of the raw material that we are going to take for the open die forging operation and closed die forging operation. See, in generally open die forging operation, whatever the volume of material of the product or final product you want to achieve is taken as the volume of the raw material. That is, volume of final product is nothing but the volume of the raw material you are taking for the forging operation. But when you talk about the closed die forging operation, you have to take, say, X is the volume of final forged product. Then if you want to take the raw material for the forging operation, then the volume of that raw material in the closed die forging operation is 10 to 20% of this volume of the final product. Okay, so why it is so? So during the closed die forging operation, we really want to confirm that the material should reach to the each and every cavity or the impression that you are having into that closed die. So once the die is going to close, we cannot see how the material flow is going to happen, where the material is flowing in case of, say, the closed die forging operation, isn't it? So for that reason, we are providing, so the volume of this raw material in case of this closed die forging is 10 to 15% more than that of the volume of the final product. Okay, then sir, you will ask the question that, sir, where this extra material is going to accommodate, isn't it? So once, no doubt, the actual volume of the component or product is X only, and that is going to fill in the cavity when we put the extra material. Now the thing is that where this extra or excess material that we have provided will go. Once these dies are closed, where the extra material will go after filling up the each and every impression or each and every corner in the die. So for that reason, see, in the closed die forging, we are providing the gutters. We are providing the gutters into the die, so that after filling off the mold cavity by this material, billet material, this excess material will go and accommodate these gutters. These are the gutters which are provided in the closed die forging. Okay, and once the operation is over, once you get the product, so this extra material is going to fill into the product, fill into the gutters, and you will get the final product like this. Okay, so this excess material will coming in the form of the flash. This is the flash, please remember. So this is the flash, and of course you want this final product, isn't it? So this is the unnecessary attachments to the main product, this in the form of flash. So this flash can be cut by the trimming operation. This flash can be cut by the trimming operation, and you will get the required product. Say this is the example of, say, coining. So pure compressive stresses is closed die forging operation. So after making the impression that is available in the die, the excess material will go and accommodate the gutters. and come in the form of flash. So that is the reason why the volume of raw material for the closed die forging is 10 to 15 or up to 20% more than that of the volume of the final product. Please remember this. Okay, dear students, now in this video we are going to see the force calculation for forging operation. The force calculation. See, so if you look at the analysis of forging operation, so the analysis of the forging operation is basically done with the two models. One is the sticking friction model and the second model is the sliding friction model. Okay, so let us take for example here, I am taking this, the open die forging operation. So here say this is the moving platen and the bottom die is the stationary platen. Okay, this is moving and this is stationary dies or platen. This is the workpiece having original diameter d original and the original height at h original. Okay, when the force is applied by this moving platen onto this the cylindrical billet, of course cylindrical billet, then what is going to happen? So when it will come down, so there you will get the increase in diameter, this is the d final, and the decrease in height, okay. So now if we apply the volume constancy principle, of course volume constancy is valid in the metal forming operation. So I can write original area into original height is equal to final area into final height. This is nothing but the area into length is the volume. So original area is pi by 4 d original square into h original is equal to pi by 4 d final square into h final. Pi by 4 get cancels. So the relation between the diameter and the heights we are getting like this, that is d final divided by d original. I can write d final divided by d original is equal to under root of h original upon h final. Okay, so now basically see the main assumption for the forging force calculation, that the force in the forging operation is the maximum at the end of the operation. Please remember, so maximum force kahan pe aayega? At the end of the operation or at the end of the stroke here. Okay, now here we have to find out the minimum initial force, F initial, of course minimum we are going to find. How to calculate this minimum initial force? That is the yield strength, or simply you can say the flow strength of the material into original area, isn't it? At the same time, if I want to have the final minimum area force F initial, then F final minimum, then it should be sigma y into A final. And you know A original is pi by 4 d original square, A final is pi by 4 d final square. Once you get this two value, we are going to have the F average, that is F initial minimum plus F final divided by 2. Now if the efficiency of forging given into the operation, general efficiency of forging is how much? 0.5 to 0.6, that is 50 to 60%. If it is given, then the F actual will be what? This F average divided by the efficiency of forging, isn't it? Now from here we got this force actual, and ahead of this I want to find out the work done or energy required in this operation, forging operation. Then it will be F actual into how much work distance it is traveled. So ये प्लेटन यहाँ से यहाँ आया, isn't it? So original height h naught and final height h final, isn't it? So you get this distance. What is the displacement actually? H original minus h final. That is the displacement of the platen, isn't it? That is h original minus h final. Okay. So this is the force and the work done. Now let us say if this forging operation and the drop forging operation, okay, having the same work done, suppose the same work done is going to done in case of the drop forging operation. Here is a weight of hammer, this is the hammer of weight W, and it is freely falling from height h onto the workpiece on the say ground. Okay, this is the workpiece. To get the same amount of work done in case of this drop forging operation, how to calculate the height of fall of this hammer? If the weight of hammer is known to you, how to calculate this height of fall? So here what is going to happen in drop forging? This potential energy gets stored by this hammer is converted into the impact energy, isn't it? No, and we know that the impact energy is twice of the potential energy in case of the sudden loads, isn't it? So for that, if I write the impact energy is equal to twice of potential energy. So what is the impact energy? It is nothing but 2 times what is potential energy is W into H, isn't it? And this is impact energy, nothing but the work done, isn't it? And this work done we are having here, we are getting from this equation. And if you put here this work done, you put here the value of this weight of the hammer W, you will get the height of fall, that is H will be equal to this work done divided by 2 times W. Okay, so in that fashion we can also able to calculate the height of fall in the drop forging operation. Okay, so this is the actually methodology to form the force, but here nowhere in this discussion we have talked about the coefficient of friction. Okay, so when the coefficient of friction is given into the equation, please remember that this force, actual force, is basically given as this F actual. We can have directly F actual कहाँ पे ज़्यादा होता है सबसे फोर्स फोर्जिंग में? एट द एंड ऑफ द ऑपरेशन और एट द एंड ऑफ द स्ट्रोक. F actual at the end of the stroke or blow or stage, end of the stroke or blow, that is F actual is given by the sigma y into final cross-sectional area, but when the friction is there, it is given as into 1 plus 2 mu Rf divided by 3 times Hf, where mu is a coefficient of friction at the die and material interface or billet material interface, coefficient of friction at die and workpiece interface, and Rf is the final radius of the workpiece. What is final radius? This is the Rf, that is df by 2, that is the Rf, and Hf is this final height, and Hf is the final height. So this is the actual force at the end of the stroke. We can get directly from this formula. No doubt we can able to derive it, but no need here. As far as GATE examination is concerned, try to have the formulas whichever we have explained in the class. No need for the derivation. Okay. So F actual here you can calculate when the coefficient of friction is given to you and asking for what they will ask, find the actual force at the end of the stroke or end of the operation or at the end of the blow. So this is how we can able to calculate the force in the forging operation. So let us see this example on the forging. A cylindrical billet of 200 mm diameter is forged from 100 mm height to 80 mm at 1100 degree centigrade. The material has the constant flow stress of 100 megapascal. So number one, we have to find out the energy required for producing the deformation. And the second bit is, if 15 kilonewton drop hammer is used to complete the reduction in one blow, what will be the height of fall? So we discussed already how to calculate the work done and the height of fall. So let us see. The initial diameter is 200 millimeter, and from the height, original height, say 100 millimeter, to the final height 80 millimeter, isn't it? So final diameter is not available with us, that we will see how much. The sigma flow or sigma y is given as 100 megapascal. Okay, we know that how to calculate the energy or work done in the forging operation is equal to this F actual into H original minus H final. We know this. So first of all, to calculate the F actual, we need to calculate F initial minimum, that is sigma y into A original, and F final minimum, it is sigma y into final cross sectional area. So for that we required final diameter, isn't it? So by having the continuity equation, A naught into H naught is equal to AF into HF. So what you got here? Pi by 4 DO square into HO is equal to pi by 4 DF square. Pi by 4 get cancels into HF. So DF will be what? DF will be DO into root of HO by HF, isn't it? Put the values. DF is equal to original diameter 200 into root of H original 100 and H final is how much? 80. So what will be the final diameter? 100 divided by 80, root of the answer, into 200. So it is 223.60 millimeter. Okay, so we got the final diameter by the volume constancy. Now here, what is F initial minimum? Sigma flow or sigma y is how much? 100 into A original pi by 4 D original, that is 200 whole square, and add force minimum at the final stage, it will be 100 into pi by 4. Diameter final stage का कितना आया? 223.6 square. So get the values. 200 square into 25 pi. It is in kilonewton I am writing, or it is mega newton, 3.14 mega newton, and it is 223.6 square into 25 pi. So it is 3.92 mega newton. Now if you have the average value, it will be this F initial plus F final minimum divided by 2, that is 3.14 plus 3.92 divided by 2. So plus 3.14 e to the power 6 divided by 2. So the average value will be 3.53 mega Newton. Okay. So once you get this force, average force, efficiency is not given. So we take directly force here. That is, F actually is 3.53 into 10 to the power 6 into the original height was 100 millimeter minus final height 80 millimeter. So it is millimeter, so convert it into meter into 10 to the power minus 3, isn't it? So how much? 3.53 into 10 to the power 6 into 20 e to the power minus 3. 3.53 into 20 into e to the power 70,600. 70600. So what is the work done? 70600. It is Newton meter, isn't it? Or it is 70.6 kilonewton meter. So after having this work done calculation, what is the next question? They are asking if the 15 kilonewton drop hammer is used to complete the reduction in one blow, what will be the height of fall? Okay. Now see, the drop hammer weight, the weight of drop hammer is how much? 15 kilonewton, isn't it? And what is work done in the case of drop forging? We know that it is 2 times W into H. So how much work done we got here? 70600. This is in a single stroke. Then it will be 2 times weight of the hammer is 15 into 10 to the power 3 Newton into H. So if you calculate the height of fall, say this is the weight hammer of the weight of the hammer, and it is falling from this much height onto the workpiece to produce the work done of 70600 Newton meter. So how much it is? 70600 divided by 30,000. It is 2.353 meter. It is 2.353 and this height 2.353 meter. Through this height, it will fall onto the work or billet material to get this much work to be done. Okay, so this is how we can able to solve the question on the force calculation for the forging operation. Now one more question I want to take here. I will not write this question. What I will do, I will read it. So listen carefully. A solid cylindrical stainless steel workpiece of 200 mm diameter and 150 mm height. This component is reduced by 50% in height with the flat die in open die forging. Assuming the flow stress of the material 1000 megapascal and coefficient of the friction is 0.2 at the work and die interface. Estimate the forging force at the end of the stroke. Options are, it is 20.8 kilonewton, 31.0 kilonewton, 78.6 kilonewton and 88.6 kilonewton. Okay, so cylindrical stainless steel workpiece of 200 mm diameter and 150 mm length. So I will draw the diagram so that you can understand. So I will write down the given data. A cylindrical workpiece between two flat dies, diameter is 200, original diameter 200, and height is how much? It is 150 mm. Okay, these are in millimeters, huh? And what they are saying, this component is reduced to the 50% height. So height is getting reduced by 50% when this moving die will come down and apply the force. So after some time there will be the increase in diameter of that is not given, but height is how much now? The height now 50% reduced, that is 75 millimeter. This is our H final. D final we have to calculate. Okay, and what is coefficient of friction? Mu is 0.2, and the flow stresses sigma y or sigma f, it is 1000 megapascal. So students, this is kind of say upsetting, isn't it? And what is given here? See, original diameter 200 millimeter, final diameter we have to find out, original height 150 mm, and 50% reduction means it becomes 75 at the end of the operation. Okay, and mu is given 0.2, flow stress is given 1000 megapascal. So first of all, let us find out the value of df, that is a naught h naught is equal to a final h final volume constancy, that is do square ho is equal to df square into h final. So what is d final? That is do under root of ho by hf. What is d original? D original is 200 into root of h original 150 divided by 70. So 200 into root 2. 200 into root 2. It is 282.84. 282.84 millimeter. This is the final diameter, isn't it? So what is the force at the end of the stroke? Always see, this is the assumption we have already learned, that the maximum force is at the end of the operation in the forging process. So F actual, we know that whenever the mu value is given, mu coefficient of friction is given. What is this F actual? This is nothing but this sigma y into final cross sectional area into bracket 1 plus 2 mu r final divided by h final. We know this. Now r final how much? This 282.84 divided by 2, you will get the r final. How much? 282.84 divided by 2, it is 141.42. It is 141.42 millimeter. Okay, so sigma y is 1000 into pi by 4 d original or the final diameter, that is 282.84 square into bracket 1 plus 2 into mu is how much? 0.2. Okay, into RF 141.42 divided by final height 75 millimeter. So calculate this and you will get the answer. So into 2 into 0.2 divided by 75, 1 plus answer into 282.4 square into 250 times pi. So it is how much? 141.42 to 0.2 into 2 divided by 75 plus 1 into, okay, यहाँ से ना. So the formula is 1 sigma y into a final into 1 plus 2 mu Rf divided by 3 Hf. This is the formula I have given, no? So it is here multiplied by 3. So you will get 141.42 to 0.2 into 2 divided by 5 divided by 3 plus 1 into 282.84 square into 250. It is equal to, you are getting 7862711.06 Newton. So it will be 1 2 3 4 5 6 78.62 meganewton. It will be meganewton. Okay, so the options should be in meganewton. See, yes, the option should be in meganewtons. Options are 20.8 meganewton, 31 meganewton, 78.6, yes, and 88.6 meganewton. So yes, answer will be what? This 78.62 meganewton. So these are the kinds of questions on the force calculation in the forging operation. Go through it. In this video, we are going to see the various preliminary forging operations. So what we are going to see now? The preliminary forging operations. So we will see it one by one. Number one is the fullering operation. So in the fullering operation, what we are doing, we are elongating the material along the lengthwise direction. So definitely increasing the cross section area and increasing the length, but it is uniformly. If you see the fullering, so suppose on the anvil, say this is the anvil. So here is, say, the lower fuller is there, or bottom fuller is there, and here is, we are having the top fuller. Okay, so here we are going to get the marks of this fuller onto this work surface. Okay, we are getting some marks here. Say this is the work, this is the top fuller, this is the bottom fuller, and this is the anvil. So in this fullering operation, we are distributing the material from center to the outward, but non-uniformly, isn't it? Distribution of material from center to outward. So because of that, what is going to happen? The length of this workpiece is going to increase, but the cross section, for example, the diameter is going to reduce. So here the force is applied, see, perpendicular to the axis of the workpiece, isn't it? The force is applied in the direction perpendicular to the length axis. Force applied perpendicular to the length axis. And of course, because of these marks of the fuller, see the marks of the fuller, we can have this non-uniform. The process is non-uniformly. To remove these marks of these fullers, what we have to do? We have to use the flattening. The flattening process is done so that we can remove the mark and we can make the part more uniform. So basically the idea is this: in the full ring operation, the material is distributed from the center to the outward direction. Length is going to increase, cross section is going to decrease non-uniformly. So this word is important here. Okay, now the next operation we are having the drawing out operation. The drawing out operation. So in the drawing out, the same thing we are going to do. We are going to elongate the material in the lengthwise direction, and we are decreasing the cross section of the component, but more uniformly. Please remember. So same process as like this, but it is uniformly. It is uniform. Please remember. So the distribution of the material from center to outward, increasing the length and decreasing the cross section, that is the diameter of the component or workpiece. This is known as the drawing out operation. Then the next operation we are having, the third operation I will take, that is upsetting. This is simply we have seen in the open die forging operation. So here the material is going to compress between the two flat dies. We have seen those operations. See, this is top die, this is the workpiece material or billet material, this is the stationary die, this is moving die, and we are applying the force, compressive force, isn't it? So that what is going to happen, the length is going to decrease but cross section is going to increase, isn't it? So this is the upsetting. The third preliminary forging operation is the upsetting. Then we are having flattening. The fourth process that we have, that is the flattening. So flattening is what? Produce the flat surface. Produce the flat surface, or to put more uniformity in the workpiece. As we seen in the full ring, the part is no more uniform. So to remove that non-uniformity, we used to have flattening after the full ring operation, isn't it? So that is producing the flat surface, that is the flattening. Then fifth we are having edging or edging. Edging, or this is also known as edging. So what is meant by this? So this is nothing but collecting the material at the ends of the given workpiece or given bar. So distribution or the collecting the material at the ends of the given bar or rod, whatever, for the operation, isn't it? So this is the edging or edging operation. Sixth one we are having, that is chamfering. Chamfering is what? Making the sharp corner into the some soft corners, that is with some radius. That is nothing but the chamfering. That is, chamfering is nothing but converting the sharp corners into smooth corners by giving the corner radius. Yes or no? Smooth corners. So this is the chamfering. Seventh one we are having the bending. We have learned this operation bending, or we are going to learn this operation in the sheet metal operations. So bending is the operation is what? Where the material is deformed along the straight axis, which is lies in the neutral plane. Okay, so bending is nothing but simply bending the component, or workpiece in a required angle. For that we are having the various dies. We are having wiping die, single edge die are same only. Wiping die and single edge die are same. Then we are having V bending die, U bending die. Like these are the various kinds of bending operation we are having. Okay. Eighth we are having the blocking or swagging operation. So what is this operation? Actually in this operation generally the rough shape of the component is produced. The rough shape of the part or component is produced. This is the blocking or swagging operation. Ninth operation is our finishing operation. It is the finishing operation. That is, finishing means what? So exact size and shape of the component is obtained. Exact shape and size of the component is going to obtain. And the last one I will write here, the trimming operation. So whatever the excessive material which have flown the circumferentially in case of the closed eyes as a flash, that can be removed by the trimming operation. That is removal of excess material. Removal of excess material from the components. For the components, for example, in bracket I will write flash is going to remove by the trimming operation. And please remember that trimming is always done after the finishing, or I can say the finishing is always followed by trimming, and this blocking is always followed by finishing. Now see, this is 4, 5, 6, 7, 8, 9, 10. So I will write once again whatever the processes we or operations, preliminary operations which have we discussed. So number 1, क्या था number 1? Fullering. Then second was drawing out. Third was upsetting. Isn't it? So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So see, if you look at these first 6 operations, so these 3 operations and these 3 operations up to chamfering. So please remember, these 3 plus 3 or 6 operations are the open die forging operations. The open die forging operations. Please remember this. Okay. The operation number 7 and 8, that is bending and blocking operation. These are semi-closed die forging operation. Die forging operation. Please remember this. And finishing is pure closed die forging operation. Closed die forging operation. Please remember, very important. And the trimming is what? It is nothing but the cutting operation. Okay, so you should know which are the open die forging operation, which are the semi-closed die forging operation, and which is the closed forging die operation. You should able to tell. Okay, now see, by using these forging preliminary operations, if I ask you to make the connecting rod which is used in the rice engine. So connecting rod is basically used by or manufactured by, not used by, it is manufactured by the forging operations only, by forging technique only. So let us, by using some of the operations in that, suppose if I give you the question like this. Suppose if I take the example of to manufacture the connecting rod. Okay, the connecting rod. So in the question, suppose if I give you the various preliminary forging operations, like say one number, if I give you the trimming, the second number if I give you the edging, the third operation if I give you fullering, fourth operation if I give you the blocking, fifth operation if I give you the finishing. So these are the operations if I give you and ask you arrange the above given preliminary forging operations in proper or correct sequence. And in the options, if I give you the various kind of sequence, so option A, B, C, D if I make, then this is a 2-mark question, isn't it? So try to manufacture the connecting rod by using this preliminary forging operation that has been given to you. So first of all, how the connecting rod look like? So it will be like this, isn't it? Okay, so this is the connecting rod. Okay, now this one we are going to produce from a given rod. So which is the first operation that we have to use here? So I hope the first operation that we have to use, that is the fullering operation. So for given rod, we have to distribute the material from center to the outward direction. So I will go for first the fullering. Then here see, the ends of these two of this rod, two ends are not same. We have to provide the necessary material at the ends. So after fullering, I will go for the edging operation or edging operation. Once I got the sufficient material at the ends, I can go for the approximate shape, that is rough shape. For producing rough shape, I will move on, that is the blocking operation given it, yes. And of course, you know, blocking is always followed by the finishing, and finishing is followed by trimming. So in that way, I can able to make the connecting rod from a given cylindrical rod, isn't it? So now if I ask you to manufacture the head of the hexagonal bolt, okay, the head of the hexagonal bolt, if I ask you to make by these forging operations, and suppose I am giving you the operations like blocking, say chamfering, upsetting and trimming, okay. So which are the operations I am giving you? Say for next example that you are going to make the hexagonal head of the hexagonal bolt, head of the hexagonal bolt. Okay, now the process I am giving to you, that is chamfering, upsetting, then blocking and say flattening. So we have to make the head of hexagonal bolt. Definitely that will look like this, isn't it? We have to make it. Okay, head, this is the head actually, hexagonal head. So definitely if you are having this material, you put in the die. Okay, so you upset it. First of all, what you will do, you are going for the upsetting, isn't it? Then you are going for, after upsetting, we will go for flattening, isn't it? First of all, we will go for upsetting, then we will go for flattening, isn't it? By the flat dies, flattening, then we will go for the approximate shape or swagging operation. Here we generally go for blocking or swagging, okay, and last one we will go for the chamfering of the edges here. Okay, these edges are going to get chamfering. So correct sequence will be first upsetting, then flattening, blocking and chamfering. So this is how we can able to make the given component by using these preliminary forging operations. Now here we are going to see the next topic, that is the forgeability. So forgeability means what actually? The forgeability. So what is mean by forgeability? The definition of forgeability says it is the ability of the given component for the forging, or the ability of the component to get forged with a little amount of force. What is forgeability? The ability of the given component to get forged with a small or little amount of force is called as the forgeability, or the ease with which the forging can be done on the component, that is with, of course, the little amount of force. It is the forgeability. Now, what is the forgeability of various materials that we are using in day-to-day life for the forging operation, or the materials which are subjected for the forging operation? We are going to see the ability of these materials. Which material can be get easily forged, or which material is very poor for forging operation, that thing we are going to see. So I am going to write here the various materials with decreasing order of their forgeability. Okay, so सबसे पहले the material is having very good forgeability is the aluminum alloy, the aluminum alloys. Then we are having magnesium alloys. After aluminum, the magnesium is very good for the forging operation. Third, we are having copper alloys. Third, we are having the copper alloys. Fourth, we are having the steel as a good forging ability. Steel. After steel, we are having the stainless steel. Okay, then we are having the nickel alloys. After nickel alloys, we are having titanium alloys. Then we are having iron based super alloys. Super alloy means these are the newly developed material having its very good properties at higher or elevated temperature. They are not going to lose the properties. These are the super alloys. Then we are having the cobalt alloys. Then we are having the columbium. At 11 number we are having tantalum alloys. 12 number we are having molybdenum alloys. Then we are having nickel based super alloys. Number 14 we are having tungsten alloys, and at the last, the material having very poor forgeability, we are having the beryllium alloys. So you can see here the aluminum, magnesium and copper, these are having very good forgeability. And if you talk about the very worst or poor forgeability, we are having the tungsten and beryllium alloys. Okay, so aluminum, magnesium, copper, steel, stainless steel, nickel alloys, titanium alloys, iron based alloys, cobalt alloys, columbium alloys, tantalum alloys, moly. We are having nickel based alloys, nickel based super alloys, tungsten, and finally beryllium. So this is actually the decreasing order of forgeability of the various material and its alloys. Okay, thank you.